and that is going to be about crater production and regolith overturn given by Emerson Speyerer. So take it away.
Okay, perfect. So if we can move on to the next slide. All right, so when the Lunar Reconnaissance Orbiter mission started, one of the primary science objectives for LROC, the last but not the least listed in the science overview paper, or the instrument overview paper, was to look for new impact craters. And when the mission was first conceived, it wasn't supposed to last a decade. And so the idea was that we would compare high-resolution observations that we're collecting during the mission to Apollo pan observations that were collected during Apollo 15, 16, and 17. And Ingrid Dalbar led an effort to actually look through the Apollo pans and compare them to the LROC NAC images. And through that work, they found a handful of new impact craters, one which is highlighted on the right-hand side. So if we can go to the next slide. So one of the surprising events that occurred during the mission was that there were two large impact flashes that occurred. One that was on March 17th of 2013, and that formed an 18-meter crater. And the second one was on September 11th, which formed a 34-meter crater. And if the image on the right was actually animated, you could actually see the 34-meter crater form on the right-hand side. But once these two events occurred, we started developing techniques to where we could actually compare narrow-angle camera images from LROC to other narrow-angle camera images from LROC to look for these type of surface changes. And so this started an effort to start scanning through systematically through the entire data set, looking for images with similar lighting and viewing geometries. And so, so far we've searched through 24,000 NAC temporal pairs, which correlates to about 3.6 trillion pixels. These are pretty large images that we're scanning through. And we're also doing other searches where we're looking for new impact craters that have formed since the Apollo mission, since the Clementine mission, since the Kikuyu terrain camera observations, as well as actually comparing WAC mosaics to other WAC mosaics, getting us an idea of the rate of larger impacts on the moon. So if we go to the next slide, this shows you what our current temporal coverage looks like. With the narrow-angle camera, we've covered about 21% of the surface. There is a little asymmetry, and that's just due to the altitude variations of the spacecraft. So we get a little bit better coverage, but lower resolution in the northern hemisphere, and a little smaller amount of coverage, but higher resolution in the southern hemisphere. So if we go to the next slide. Okay. So on the right-hand side, you can see what the crater production function looks like. This is derived from the 24,000 NAC temporal pairs. This plot is a little over a year old, so there's a few more craters that we've found with the NAC that aren't included here. But the red line is the one-year isochron estimated from the Neucomb production function. And so you can see that, you know, we overall agree with it pretty well. We are still getting a steeper slope in the 10 to 20 meter range. And so we're still trying to investigate that. And so that's still a work in progress. And as the mission goes on, we'll be able to refine that further. And that's why it's also important to look at these other data sets. So if we include the WAC craters as well as the Kikuyu craters and the Apollo craters, we can try to refine that rate for a larger diameter range. So next slide. So one of the things that was discovered when we first started looking at these impacts, this is an example of a temporal ratio image, similar to the one that Brett showed earlier, of an after image divided by a before image. And from that, you can see that there's 4 different zones that are identified around that crater. If we go to the next slide, I actually added arrows to indicate where those are located. And so there are 4 distinct zones and around this one 18-meter crater. And then when we started looking at the hundreds and hundreds of more craters that we were identifying across the moon, we were also seeing a variety of craters that had all 4 zones. Some of them only had 1 or 2 zones. But it was an interesting discovery that we made. So if we go to the next slide. So one of the outstanding questions that's coming out of this work is, how large of an area is affected by these newly formed impacts? We saw in talk 2 before me where they were showing these diviner cold spots that go over such a large area. And in fact, some of these large craters, including this one here, are actually showing up as diviner cold spots. And so we have a great understanding of what's happening close to the crater, but there's still questions that need to be addressed as we work our way out into more of the distal zones. And this affects not only our interpretation of remotely sensed observations, but could also be hazardous to future astronauts. And to just give you a sense of scale, hopefully your screen resolution is good enough, you'll see that white little dot right at the center there. That's actually the crater. So the crater is 70 meters in diameter, and these distal rays that are going from it extend out over 100 kilometers. So some of these impacts are actually changing quite a large area. So if we move on to the next slide. So one of the other discoveries that was made with the March 17th impact is this collection of sparse distal ejecta, which were called splotches. And these are local changes to the surface reflectance. There's no actual visible rim in any of these features. And there's several different hypotheses for how they could form. One is that they could be a swarm of small primary impacts that were coming with the major bolide that created the 18-meter crater, or they could be unrelated primary craters that have formed just around the same time, or they could be small secondary impacts. And so, and we believe that many of these are going to be small secondary impacts because some point actually back to the crater itself. In fact, that's how the location of the crater was first found. We're first looking at observations that were too far to the west, and then we could kind of see the direction of how these splotches were emplaced, and we could point it back to the primary crater. And some of this is correlated with the ray structure itself. So if we move on to the next slide. The temporal pair isn't blinking right now, but you can kind of see the ratio image. So you can see that there's really no rim feature in the ratio images at all. And so it's just an interesting thing. But one thing to note is that many of these are low reflectance, so about 90%, and they just change the reflectance ever so slightly, only a few percent. But when we have these high reflectance splotches, which are a much smaller population, they're actually increasing the surface reflectance quite a bit, like 10%. So the next slide shows the global distribution of these new impacts, or these new splotches. So we've so far counted 120,000. And I'll quickly move on to the next slide, since I'm not sure how much time is left. And so there's, okay, 2 minutes. So there's still questions remaining on, what the impact of all these distal secondaries are. And so the idea right now is that you have this material that's coming out from the primary impact crater, and it's actually churning the surface. And when the mature layer is really thick, you're just kind of roughening up that surface and creating that low reflectance splotch. But on the right-hand side, you can see an example where the mature layer is really thin, and you're actually bringing up the brighter immature material, and therefore creating a high reflectance splotch in this case. And so that's kind of like the formation mechanism that we're kind of looking at. But what we've also seen is, based on that coverage that I showed you on the previous slide, that these can actually cover the entire moon in less than 100,000 years. So it's a pretty quick rate of coverage, but there's still questions that remain. There's been some modeling work, but there's still questions to remain on how deep, to what depth these sparse distal secondaries are able to churn the regolith, and that can impact both space weathering, actually the presence, and how well you can keep surface volatiles, and they could also be potentially hazardous. So we'll move on to the final slide. And so basically these temporal images are a really good resource for not only identifying some of these newly formed impact craters and distal secondaries, but also characterizing this. We've done a lot of work that wasn't shown here in this presentation on the photometric properties of these new impacts and what we can discern from the different cratering mechanics. So with that, I'll take any questions, or we can move on to the next talk.
All right, thanks, Emerson.